this video, we are going to talk about the importance of channel power and adjacent channel power, their role in spectrum analysis, and how you can use the Signal Hound Spike software to perform these measurements. The most common way to make power measurements with a spectrum analyzer is to use the trace marker. In the Spike software, a marker can be placed by clicking anywhere on the graticule or by pressing the peak search button. The marker provides the user with a frequency and power at that sweep bin location. Unfortunately, the marker's usefulness is limited to primarily CW-type signals or where the resolution bandwidth exceeds the modulation bandwidth. When it comes to modulated or spread spectrum waveforms, the marker will no longer be adequate for measuring power. Here, we are looking at a 20 MHz wireless LAN signal with an output power of -10 dBm. The energy of this waveform is spread out across several frequencies through the use of Ofdm modulation. When a marker is used in this scenario, it is only reading the power at this one specific frequency. What if we want to know the total output power of this signal? Here is where channel power comes into play. The equation for an integrated bandwidth channel power measurement is shown here. The channel power measurement sums all frequency bins within the user-specified channel bandwidth. The summation is performed in linear units. The FFT window bandwidth is divided out, and the result is converted back to log scale. The channel power measurement is enabled in the channel power dock. The channel power integration bandwidth or width can also be specified. With the channel power measurement active, you can view the measurement result here. It matches our expected output power of -10 dBm. The channel power measurement is useful for verifying a wireless signal is within its defined minimum or maximum power range, as defined by its specification. In an over-the-air measurement, the signal of interest may be part of a protocol which transmits short packets or bursts of energy, making it hard to reliably measure channel power with this method. For this, we can utilize the zero-span method of calculating channel power. After switching into zero-span mode, we need to specify a sample rate and bandwidth to match our signal bandwidth. We also need to set up a video trigger level that allows us to capture the short pulse that we want to measure. Using the time overview plot, we can narrow in on the waveform so that only the on period of this transmission is shown in the AM versus time plot. The AM versus time plot calculates the average power over the measurement interval. This gives us the channel power of the pulsed waveform. A common measurement performed in conjunction with channel power is adjacent channel power ratio, also known as adjacent channel power leakage ratio. Adjacent channel power measures the ratio of power between the channel and an adjacent channel. The most common use case for this is to measure effects common to transmitters such as nonlinearities, spectral regrowth, and other non-desirable emissions. Wireless standards will specify how much power can be transmitted in adjacent channels. Spike provides an easy-to-use adjacent channel power measurement. With the channel power measurement active, users can activate up to 5 adjacent channel power pairs. Each pair can be individually activated with their own offset and widths. Results are provided in a tabulated view. These measurements come standard in the Spike software with the purchase of any Signal Hound spectrum analyzer. Thanks for watching. To see more videos like this or to learn more about our products, visit us at signalhound.com.